Hello student, I'm Mr. Leung. So in this video, we are going to talk about the long questions in Chapter 9 assignment. So they are question 7 and question 9. So in question 7, we are going to study the graph below. So in this graph is showing the oxygen production rate and the carbon dioxide production rate of a local plant on a summer day. So what you can see is that in the x-axis you will find the time, okay, or 2 a.m., 4 a.m., 6 a.m., and then 12 noon, okay, and then 10 o'clock, okay, and then 12 o'clock. So and then for the y-axis, it will be the rate of gas production. So it can be the dotted line for the oxygen production, and also for this concrete line for the carbon dioxide production. So in this part, in this graph, so what can you see is that it will cause us the assumption of the respiration rate in a plant, because what you can see is that throughout the whole day, the rate of respiration is relatively constant. How can we know that is respiration? Because this line is referring to the carbon dioxide production. So which process will produce carbon dioxide in the plant? Which is respiration. So on the other hand, for the dotted line, oxygen production. So that's why for this dotted line is referring to the photosynthesis, right? And the photosynthesis, it is affected by the light intensity. So what you can see is that, for example, 6 a.m. 6 a.m. the sunrise, and then for the 12 noon, the light intensity is the highest. So that's why the oxygen production will also be highest, because the photosynthesis rate is the highest. And then, for example, for 7 p.m., okay, sunset, so no light anymore, and then no photosynthesis at all. So that's why you can refer to the timeline and then think about, when will the plant start doing photosynthesis, okay? So for part A, state the time at which there is no net gases exchange in and out of the leaves. So that's why for A, you need to think about what does it mean, no net exchange of gases. It means compensation point, because at this point, at this certain light intensity, the rate of photosynthesis is equal to the rate of respiration. So that's why there will be no extra carbon dioxide production and no extra carbon dioxide uptaken from the atmosphere. And the same case for oxygen. So that's why you can find these 2 points. Okay, I circle it for you already, the intercept point of these 2 curves. So what you can see is that you draw a straight line to the x-axis, and then you will find the time. So just tell me the time, the exact time will be okay. Maybe 6 o'clock, 7 o'clock, 8 o'clock, something like this. But with AM and PM, okay? Not just tell me, 10 o'clock, 10 AM or 10 PM? I don't know. Okay, refer to the x-axis, okay? So that's for part A. And then for part B, sketch a line on the above graph. So that's why for answering B part, you need to copy this graph first, and then sketch another line, okay, maybe by using another color, okay, so on the graph, so to show that the oxygen production rate of a plant on a winter day. So on a winter day, how is it so special? So in this graph, it's talking about on the summer day, okay, so on the summer day, the daytime, the light intensity, and then the temperature is totally different from the winter day, right? So that's why, for example, on winter days, the daytime should be relatively shorter. That means the sunrise will be a bit later, and then the sunset will be a little bit earlier. The daytime will be shorter. And then the temperature is also relatively lower. So what will it, okay, or how do they affect the rate of the photosynthesis of the plant, okay? So of course in this question, it used another way to represent photosynthesis. It used the rate of oxygen production, but actually you know that, okay, it means photosynthesis. So that's why copy this graph and then draw another line for me, sketch another line. Now sketching, that means you do not have the data at all. You don't know that it can produce 10 units of O2, 5 units of O2. No, you do not have the number, but you can tell me the relative position will be the new curve. Okay, will it be narrower, or will it be taller, shorter, or broader? Okay, so you tell me. Then for part C. Part C is talking about the area below the line showing the oxygen production rate is usually greater than the area below the line showing the carbon dioxide production rate. So for this part, what does it mean? It means that the area below the line showing the oxygen production, that means the dotted line. Okay, the area below this dotted line, that means this area, right? And then for the area below the line showing the carbon dioxide production, that means this area. Okay, so actually what does it mean? You need to recall the meaning of oxygen production and carbon dioxide production first. Oxygen production, as what we say, photosynthesis. Carbon dioxide production, okay, actually you know that is respiration. So that's why it means that the area showing the photosynthesis is usually greater than the area of respiration. So what does it mean? Other than the gases involved, okay? So that's why in part C, we think out of the box. We are not talking about oxygen and carbon dioxide anymore. We talk about food. So think about that. Photosynthesis is food production or food consumption process. Meanwhile, respiration is either food production or food consumption process. Like, you tell me first. That you need to think about this question first, okay? Or photosynthesis, food production or food consumption, okay? And the same question for respiration. So after you know that, so you can answer the question for me. So the area below the line showing the oxygen production rate represent food production or food consumption. And for the area or the line showing the carbon dioxide production rate represent the food production or food consumption in one day. So that's why for these 2 marks, you answer me first. And then for the third mark is that also it's important for the food production to be smaller or greater than the food consumption, so that there will be a net amount of food produced. So that's why the production, okay, what should it be? Smaller or greater than the food consumption. And the last mark, as a result, this provides energy for the plant to survive, to grow, to produce fruit. You have the last sentence already. So for the first 3 statements, you think about the question I asked you. Okay, so O2 production, CO2 production, photosynthesis, respiration, food production, food consumption. What is the relationship among them? Okay, so after you think about this, so you can construct the whole paragraph for me. So that's question 7. So for question 9, question 9A1 is a bit easier because it's talking about the leaf structure. So for the whole question, it's talking about to compare two different types of leaves. One type of leaf, okay, the leaves that develop in shady place, okay, we call it shade leaves. And then we found that the structure, okay, and then the biochemical reaction, the metabolism in the shaded leaves, they are different from the leaves that grow in sunny place. So that's the sun leaves. So it's just a name to describe shaded leaves, okay, the leaves growing in a shady place. The sun leaves, they live in a sunny place, just a name, okay? So, and then for the photomicrograph, you can see that that's the cross section of the leaf growing in a shady place. So it should be the shaded leaves. Okay, so for this part, it should be for the shade leaves. So the basic structure, okay, are given already, okay, especially the parasite mesophyll cells, because it's related to the question. So with reference to 2 features observed in this photomicrograph, describe how the leaf is adapted to allow the palisade mesophyll cells to obtain the gas required for photosynthesis. So you can see that how tricky is this question. It doesn't tell you which type of gas the plants required for photosynthesis, but you know the plants, they need carbon dioxide for photosynthesis, right? But the question intentionally hide this message from you. But of course, you are clever, so that's why you know carbon dioxide is required. Okay, so that's why the question will be, how can the leaf is adapted to allow the palisade mesophyll cells to obtain carbon dioxide for photosynthesis? So that's why there are 3 guiding questions for you. Take a look at the leaves, and then you think about these 3 questions. How can the gas diffuse into the leaves? Any hole on the leaf surface, no matter on the upper and lower leaf surface, any hole? And then for the second one is that after the gas diffuse into the leaf, so how can the gas, they can really diffuse in the leaf so freely and quickly to the palisade mesophyll cells? So any space in the leaf for the gas to move? And the third one is that how is the thickness of the leaf helping the gas to diffuse inside the leaf so quickly? So that's why for the thickness, it's either thick and thin, or thin, right? Either thick or thin. So that's why you tell me, oh, the leaf should be thick or the leaf should be thin. You tell me the answer. So by thinking about the guiding question 1, 2, 3, refer to the leaf structure in your textbook. What do you have? You have the stoma already. You have the air space already. So that's for the first 2 questions, right? But for the third question, you answer me. So that's why the presence of something allows the carbon dioxide to diffuse rapidly from the atmosphere into the leaves. And then there is a large something among the spongy mesophyll cells to allow the carbon dioxide to diffuse freely, quickly to the palisade mesophyll cells for photosynthesis. And the leaf is thin or thick, which reduce the distance over which the carbon dioxide has to diffuse from the lower parts of the leaf, from the lower side to the palisade mesophyll cells for photosynthesis. 1, 2, 3. Although the question carries 2 marks, you can answer the third statement. I give you 1 more bonus mark. So that's for A1. And then for A2 is talking about the sun leaves of the plant has a thicker cuticle than its shaded leaves. So why is it so important for the sun leaves to have a thicker cuticle? So in this question, of course, we need to recall the cuticle function first. Cuticle, the function is that it reduces the water loss from the leaf surface, no matter on the upper surface or lower surface. So that's the basic function. So that's why in the sunny place and in the shady place, what is the difference of the light intensity? What is the difference of the temperature? And also the rate of evaporation of water. So after you can answer me these 3 questions, sunny place or the temperature is higher or lower lah, or the sunny place the temperature is higher or lower lah, and then so what will be the rate of evaporation of water in the sunny place leh? Also higher or lower leh? You tell me. So that's why you can construct your answer like this. Being always exposed to a high light intensity, that the sunny leaves have a higher or lower evaporation rate. So the concept is that I add question 2 for you as a linkage between the light intensity and the rate of evaporation. Think about 1, 2, 3, the whole logic. It can help you to finish this statement. And then for the second statement, it's given the thicker cuticle can prevent the sun leaves from excessive loss of water. Now remember, it's talking about reduce water loss. Reduce water loss is correct. Prevent excessive water loss is also correct. But if you tell me the cuticle can prevent the water loss, it's not correct. Prevent excessive water loss, but not only prevent water loss, because it's impossible to prevent water loss. We shall talk about a bit more in chapter 10. But now you know how can you write your sentence first. And then for part B is also taking a look at the graph lah. So for this graph, it's just a simple graph we talked about before. Okay, it's talking about just like this. Okay, the typical graph in question 5. So the similarity, okay, we talk about it for many times that, okay, for the net uptake of carbon dioxide of the plant, that means we need to compare the rate of the photosynthesis and the rate of respiration. For the photosynthesis is higher than the rate of respiration, it means there will be net uptake of carbon dioxide above zero. Photo is faster than resp, and resp faster than photo, there will be net release of carbon dioxide. Resp faster than photo, below zero, net release of carbon dioxide. Okay, right? And above zero will be net uptake of carbon dioxide. Okay? So for this very typical question, so we can find that what is the implication? That means what's the meaning behind of having a positive net uptake of carbon dioxide for a plant? So we call that, okay, we recall the concept we learned in the graph. The positive net uptake of carbon dioxide implies that the rate of photosynthesis of the plant is higher or lower than its rate of respiration. So tell me this part, okay, higher or lower. Or you can refer to the other concept, okay. So the bonus part will be that a positive net uptake of carbon dioxide implies a net what? A net food production or food consumption in the plant. So if you answer the first question, of course 1 mark already. But if you can also answer the second statement, you will earn 1 more bonus mark. Okay? So that's for the question 9B1. And then for B2, we are going to compare the compensation points of these two types of leaves. Okay? So we can compare this curve and this curve. That's the first part of the question. And then the second part is that to explain how this plant species can adapt to live in a shady place. So we call the concept of compensation point first. Compensation point, it means at a particular light intensity, the rate of photosynthesis is same as the rate of respiration. Now we call this very important concept first, okay? And actually we talk about it for many times already by using the MC or by using the long question. So for this part, by comparing the curves, okay? Now remember the first part of the question is to compare, so compare the curve of the leaf in sunny place and then the shade leaf, okay? So you can find the compensation point. That's the intercept point of the curve and the x-axis, the light intensity here, okay? So that's why you can refer to this orange, the intercept point, and also the blue, this intercept point. Not this one, not the intercept point of the curve themselves, but the curve or at the curve and the x-axis, so this point and this point. So which type of leaf has the lower compensation point? Okay, that means it requires lower light intensity to attain the compensation point. Okay, the rate of respiration is same as the rate of photosynthesis. Okay, so compare first, and then explain any special meaning, so that's why any importance behind that. We talk about the right hand side first, okay? On the right hand side, that's the logic flow. So we talk about case 2 first. So when the light intensity reaches the compensation point, it means that the rate of photosynthesis is equal to the rate of respiration. And then for the case 1 is that So what about the light intensity is lower than the compensation point? So that means the plant, okay, it may still carry out photosynthesis, but the rate is lower than the respiration, the rate of respiration. But for the case 3 is that once the light intensity is higher than the compensation point, so that's why the rate of photosynthesis will be higher than the rate of respiration. Now these 3 basic concepts and these 3 basic logic flow you must understand first by analyzing the graph. Okay, so you can see that the light intensity, okay, higher than the compensation point, okay, like at point C, okay, at this particular light intensity, it reaches the compensation point. So for D and E, higher light intensity, so photo faster than resp. And then for AB, the light intensity is lower than the compensation point at this particular light intensity and point C. So that's why resp will be faster than photo. So go back to on the left hand side. So I give you one example, okay, and then you will understand everything. So we have 2 plants. Plant A, its compensation point is 3 units of light intensity. And for the plant B, its compensation point is 7 units light intensity. So that's why we increase the light intensity bit by bit to the plant, and let's see what will happen. So 0 light intensity, that means no light. So no photosynthesis. So that's why only respiration, right? Resp faster than photo. And then for light intensity 1, the plants, they start doing photosynthesis, but the rate should be lower than the respiration. Okay, and then 3 units of light intensity, it reaches the compensation point. So that's why P is equal to R. Photosynthesis is equal to the rate of respiration. But at the 3 units of light intensity, okay, because the compensation point of plant P is 7, so that's why it's still lower than the compensation point. So that's why photo is lower rate than the resp. And then 5, 7, 9, 11, and 13. So we can see that from the 5 units of light intensity, so the plant A can have a higher rate of photosynthesis than the respiration already. However, plant B, it needs to wait until the 7 unit light intensity to attain the compensation point. And then from 9, 11, 13, okay, the rate of photosynthesis is faster than the respiration. So that's why the logic is that if the compensation point is lower, right, so it can attain the compensation earlier than the other plant, okay, because even a low light intensity heading, okay, to attain the compensation point, and then after the compensation point, its photosynthesis rate is higher than the rate of the respiration. But the plant B, it needs to wait, okay, wait for a higher light intensity. So that's why we go back to the questions. The question is talking about first part, compare the compensation point. So by using the graph, tell me the answer. Leaf of the species P grown in a shady place have a higher or lower compensation point than those in sunny place. First question. Second question, explain how this plant, shady or sunny plants, can adapt to the shady place, and how to adapt. Okay, how is it so important? Because this ensures that shady or sunny plants can attain positive growth in an environment with low light intensity. So remember that positive growth, it means if the plant, it can carry out photosynthesis at a higher rate than respiration, so it can make more food, right? Make more food, and then more food can be used for survival, for growth, for making fruit, something like this. So that's why question 1, question 2, I mean 2 parts, okay, in this part B, part 2 question. Okay, So for the last part, now this question is talking about the design of the experiment. Okay, no worry, I will show you all the steps one by one to think about it and then all the answer. Okay, all you need to do is to understand and then copy. So by using the hydrogen carbonate integrated solution, design an experiment to compare the compensation points of these two potted plants. So illustrate the setup. That means you need to draw something with a labeled diagram. Okay, you also need to label. So before we talk about the drawing, okay, we talk about the basic design first. So that's why we need to think about, what is the function of the hydrogen carbonate integrated solution? This integrated solution is used to determine, okay, the carbon dioxide concentration, and then you will see the color change, okay, of the indicator once they are put in different carbon dioxide concentration. Equals to 0.3 red, higher than 0.3% red to yellow, and lower than 0.3% red to purple. And then actually what we are going to observe is the compensation point. And recall the concept is that at the compensation point, the rate of photosynthesis is equal to the rate of respiration. So that means there is no net gas exchange in the plant. So that's why the carbon dioxide concentration in the boiling tube, for example, should be remain unchanged. Okay, so that means it should be equal to 0.03%. So that's why the solution, what we need to find, should be remains red. Okay, understand the concept. And then for the second one is that we also need to think about the DV, IV, CV. Okay, so that's why for the DV, okay, that's something we need to observe, to measure. But my question, you also need to think about, because we are going to design the experiment, how can you observe? Not only what are you observing, what do you want to observe? No, I know I want to observe what thing. But the next question is, how can I observe it? Okay, so and then for the IV, how can you manipulate the variable? How can you change it? I know IV, that's something I change. But how do I change it? How? Okay, what do I do? Okay, that's the question. And then what are the CV lah? Okay, and then how can you keep them constant lah? So that's the DV, IV, CV, the whole experiment. Okay, in the DSE question, okay, we always miss such question. Design the experiment. IV, CV, DV. You must understand them first. And then just take a look at this table lah. For IV, DV, CV, for the DV is that you can see that what we are going to observe to compare compensation points of the plants. So that's why, what are you observing? I'm going to observe the compensation point of the plant. Done. But how can you observe it? So the question asks you to use the hydrogen carbonate indicator. So how can you determine that? Okay. Okay. And when the color is like this, is at the compensation point. And the color is like this and like this. It's not yet the compensation point. Okay, we call the color red, yellow, and purple. Okay, so actually I also explained it already. Okay, and then for the IV, because we are observing the compensation point, and compensation point is talking about a particular light intensity, right? So that's why the factor we change is the light intensity by increasing at this point, compensation point. Okay, and then how can you manipulate, control this variable? So imagine that if you have a light bulb, okay, as the light source. So how can you change the light intensity you supply for the plants? Okay, how can you supply a stronger light or a weaker light? Okay. And then for the CV, the factors are kept constant in both setup to make sure that the investigation is a fair test. So for example, temperature. So someone may challenge you, it has different, they have different compensation point due to the temperature because temperature it will also affect the rate of photosynthesis. So that's why you are wrong. No, I keep temperature constant. Sorry. So that's why I only change the light intensity. So that's why if I can observe anything difference of the compensation point, it should be due to the light intensity but not the temperature. Okay, so DV, IV, CV. And then take a look at the drawing. Okay, no worry, bit by bit, the whole step will be shown. So these two questions are the one we are going to explain a bit more. Okay, and then also you need to think about it. So for this part, okay, draw the workable setup. Okay, just like the typical experiment. Okay, in the textbook, we pick a leaf. Okay, we pick a leaf and then put it in the boiling tube. And in the boiling tube, we have the hydrogen carbonate indicator already. And then of course, okay, keep the CV identical, temperature of the environment. And then put a lamp, okay, just maybe next to the boiling tube, okay. So and then for the third one is that because we need to shine the light on the plant, okay, and then look for the compensation point, right? So that's why we need to keep change the light intensity, okay. But how can we observe, okay, the result, okay? We need to give them some light first. So that's why subject the setup to a very low intensity of light first. So maybe for example for 30 minutes, okay, and then note the color of the indicator. Or maybe the light intensity is just so low. So that's why both of them become yellow, okay, because more carbon dioxide will be inside, become yellow from red to yellow, okay. But what if we keep changing the light intensity? Okay, so for example, repeat the step with increasing light intensity because we need to make it higher and higher. Okay, so by reducing the distance between the light source and the plant, and also adjust the dimmer control to increase the brightness of the light bulb. Okay, so that's the possible ways for you to manipulate the variables, right? We are going to change the light intensity, but how can we change it? We need to tell other people the method we use. Okay, so also we need to note the color of the indicator. Okay, or changing the light intensity and then take a look at the indicator. Okay, after maybe 30 minutes. Okay, so and then determine the light intensity because maybe for example for plant Q, okay, from the light source, okay, it moved to this distance, and then the indicator solution, it remains red already, but maybe on the plant R, okay, it doesn't remain red at all. Okay, it's still for yellow, not purple, yellow. Okay, higher CO2. So that's why I need to move the light bulb, okay, much closer to the boiling tube. Okay, and then find that until the setup, both of the setup, okay, the indicator remains red. That means they attain the compensation point. And then finally compare the light intensities. Okay, so for example for plant Q in this part, okay, longer distance, that means lower light intensity, right? And for plant R, shorter the distance, but that means the higher the light intensity. So that's why the compensation point of R is higher than the compensation point of Q. So you can compare it. Okay, so now what you need to copy is 2, 3, 4, 5, 6. Okay, now for one is for your drawing. You just copy this whole setup will be fine. The boiling tube and the leaf and the light bulb. Okay, and then the distance between the light source and the plant. Okay, and then you draw the workable setup already. But I want you to illustrate with labels. Give me the label, even the lamp. I want to know is a lamp. Okay, so that's why that's for the question 9. Okay, so if you have any question, leave it below. I will answer you as soon as possible. See you next time. Bye bye.